Exploration of triple integral in spherical coordinates. In a spherical coordinate system, a point P in space is represented by n order triple rho, theta, and phi. Rho is the distance between the point and the origin. Theta is the angle counterclockwise from the pole or positive x-axis in the xy plane. This is the same as cylindrical coordinates. Phi is the angle between the positive z-axis and the point. Next, this is converting between spherical and rectangular coordinates. It's spherical to rectangular and rectangular to sphericals. The other relationships that are important to know for conversions are r equal to rho sine phi, theta equal to theta. These equations are used to convert from spherical coordinates to cylindrical coordinates. Z equal to rho cos phi and rho equal to square root r square plus z square. Theta equal to theta. These equations are used to convert from cylindrical coordinates to spherical coordinates. Phi equal to r cos in bracket z divided by square root r square plus z square. Next, let's take a look at triple integral in spherical coordinates. If we have a triple integral in rectangular form, as we can see, this is how we write in the spherical coordinates. And there are several things that we should recognize here. First, the function must be expressed in spherical coordinates. Rx is equal to rho sine phi cosine theta, is equal to rho sine phi sine theta, z is equal to rho cosine phi. Notice that differential v is equal to rho squared sine phi d rho d phi d theta.
I'm going to present the introduction of Stokes theorems. Stokes theorems help us with closed curve in 3D dimension where the curve of the boundary of the surface S. So, we can assume that the curve is in the positive orientation and goes in the counterclockwise direction with respect to the normal vector of the surface, which is n. To find the amount of field that goes in the direction of the curve, we need to take the line integral of f along C, and Stokes theorem also gives us another method to find the line integral, which is equal to surface integral at the curl of f dot n over the surface S. So, we can express the Stokes theorem using these equations. And we can find the curl f by using the equation below. Equation of Stokes theorem in electricity, which is Ampere's law. Ampere's law is a law of physics that relating current to the magnetic field, provided that the electric charge density is independent of time. It can be written in a differential or integral version, which is related by Stokes theorems. As we can see, there is Stokes theorem formula and Ampere's law formula. After we apply the Stokes theorem formula to the Ampere law formula, we get the equation below. Consider that B around the straight wire carrying current, which is I. Symmetry indicates us that the B is oriented in the theta direction in RHS screw sense with relation to the current. So, inside the wire, the bounding only encloses the fraction, which is pi r square over pi a square of the current I. So, we get H.
Hello, my name is Wong Jiang. Today I want to talk about application of triple integral in spherical coordinate, which is Ampere's law. The differential of Ampere's security law of magnetic indicates that the volume current density at any point in space is proportional to the spatial range of change of the magnetic fields and is perpendicular to the magnetic fields at that point. So, the volume calculated from triple integral in spherical coordinate can be multiplied by current density given to get the volume current density. Madam may pause the video to record the application. Let's conclude. The Ampere laws indicate that the volume current density is proportional to the spatial range of change of the magnetic fields and is perpendicular to the magnetic field. This was our explanation of question triple integral in spherical coordinate. Determine the volume current density between the outside of small sphere x squared plus y squared plus z squared equal to 1 and inside of the big sphere x squared plus y squared plus z squared equal to 4 when the current density given is 6. Refer to the Malek or sphere. The answer for volume between the outside of small sphere and inside of big sphere is 28 pi over 3 meter cubed. To verify our answer, we direct using the volume of big sphere minus the volume of small spheres and equal to the same answer, that is 28 pi over 3 meter cube. To determine the volume current density, we using the current density given, that is 6 over the volume calculated just now, and we get the final answer 0.2046 C per meter cube.
Example of Stokes theorem. The question says that f x y z equal to negative y x z. Let S be the part of parabola z equal to 7 minus x squared minus 4y squared that lies above the plane z equal to 3, oriented with upward pointing normal. Use Stokes theorem to find surface integral curl f dot ds. So for the line integral f dot dr equal to line integral formula, which is FRT dot product R prime T dt. Next, we sketch the parabola equation in terms of 3D dimensional view. So the parabola will be in this form. So here is S, which is z equal to 7 minus x squared minus 4y squared. So this will be C. C is the boundary of S. C will be this part with positive direction. So the circle is x squared plus 4y squared equal to 4. Z is given, which is 3 here. So the parametric equation for the circle is RT equal to 2 cos t sin t and 3. 3 is given. So we need to find R prime, which is negative 2 sin t, cos t, and 0. Then based on the formula, we need to find FRT. F is negative y at z. So we substitute sin t into negative y, which is negative sin t, and then 2 cos t and 3. We need to dot product with r prime t. The dot product means we need to multiply each component of ijk to their component of corresponding component. So the answer will be 2 sin squared t plus 2 cos squared t. The limit will be 0 to 2 pi because of the complete circle. We take 2 out from the limit. So sin squared t plus cos squared t will be 1. And substitute 2 pi, then the answer will be 4 pi. That's all. Thank you.